Good afternoon, everyone, and welcome to this new session for the CHIPS think tank. This is a series of webinars, which is brought to you by the aCCCCess project. So it gives you insights and reflections on the semiconductor industry from European opinion leaders. And today, I'm very pleased to welcome Pekka Pursula, who is VP Microelectronics and Quantum Technology at VTT Finland. So welcome, Pekka, and thank you for being with us today.
Thank you for having me, Regis.
So the previous sessions are available. So you have to connect on the YouTube channel, on the YouTube link. You can scan the QR code on the right of my screen so that you can see, you can go straight to the YouTube channel. Okay, this is an interactive session, so of course you are very welcome to participate, ask your question, to react. You agree, you disagree, but we want to hear from you. We want to hear your thoughts. So let's tell us what you think about everything that we say today. We like when these sessions are very interactive. And so today we are going to talk about the Europe's quantum momentum. I'm Regis Amonar, CTO of Blue Morpho. I'm coordinator of aCCCCess. And again, I have the pleasure to have today Pekka Pursula. So the aCCCCess project, a few words about that. We are a consortium of 7 partners funded by Digital Europe under the CHIPS GU program. And the project lasts for 4 years. We are already 1 year behind. And it's a budget of 4 million for 4 years. You can see here on the right all our beloved associated partners. And the competence centers, there's 1 competence center per country. So you have 2 in Spain and lucky in Belgium as well. So there are 30 in total competence center, CHIPS competence center, which are hubs of excellence, where you can find expertise in technologies, support in training, and also facilitation to access to venture capital. And we have a dedicated action in collaboration between aCCCCess and all the competence centers. So you have 30 points on the map, but they are all actually connected through the network of aCCCCess. And on the right, you can see all the pilot lines, which are more and more integrated into our action. Okay, so talking about interacting, we would like to know more about you guys. So we would like to know who you are. So are you a startup? Are you a large corporate who wants to know more about quantum? Are you an investor, or are you part of the CHIPS Competence Center? So I give you a few seconds to answer this questionnaire, and I see people are replying. So let's wait for a few more seconds, and almost everyone voted. So let's close the poll. And let's look at the results. So we have a majority of CHIPS competence centers, 14% of startups, 8% of large company, no investor in the room today, and for about 20%, something else than all the different beasts listed above. Okay, so thank you very much. It's very helpful to know you better and to interact with you. So let's talk a little bit about Finland. Finland, it's 5,657,608 people. It was estimated in January 2026 that they didn't say at what time they estimated the number of people. The semiconductor industry in Finland is about 5,000 employees, and the top 100 companies in Finland have invested 9 billion euros in R&D. So a country which is very much oriented towards innovation. And actually, Finland is, for the 8 years in a row, the happiest country in the world, which is really a success. So I think that my first question for you, Pekka, is: are you happy, man? Are you happy today?
Of course, I'm happy. I'm a Finn. So
Yeah, so all the Finns are happy. Okay,
yeah.
so can you introduce yourself? Can you tell us a little bit more about yourself? What is your responsibility at VTT in Finland?
Yes, thank you, Regis, and welcome everybody to this webinar. Thank you for having me. So, so my name is Pekka Pursula. I'm the Vice President of Microelectronics and Quantum Technologies at the VTT Technical Research Center of Finland. So we have 250 people working at VTT on the microelectronics and quantum technologies. We run our own clean room and a fab where we do this development. So I would say that we are very much focused on chips and hardware, both in microelectronics and quantum, of course, also extending towards the applications in certain areas, but very focused on technology development. And my role as the vice president is, of course, to lead all of this activity, to look into on the other hand, on the daily operations, ensure that everything goes, but especially on the long-term development of these topics and our roadmaps. Where do we want to go? And in this role and my previous roles too, I have been very active on taking this, especially in quantum technology field, this thinking that how do we get quantum technology also industrialized and a mature technology as we have the other microelectronic technologies from photonics to CMOS to so forth. CMOS is of course the kind of ultimate goal with all the yields and mass production, but this is clearly the time that the quantum technology now needs to move from research labs to really into industrial use, and this is very much been on my agenda for years, and I'm enthusiastic about.
Excellent. And what is your connection with the quantum pilot line? Can you position yourself with regard to this?
Indeed. So now the as part of the European Chips Act, quantum stability pilot lines are being set up on a European level, and there are several of those, and I'm the coordinator of the superconducting quantum pilot line. So I have a bit more on that later on.
Okay, so I think that you have a presentation for us about the pilot line. So you can now share your screen.
Okay, I will be sharing my screen.
Perfect, we can see.
So do you see now my slides?
Yes.
Excellent, great. So following the title of today's session, I also have in my presentation kind of two parts. We start a bit about the Finnish quantum technology ecosystem first, and then extend to the European view and the European quantum pilot lines. So starting with the Finnish ecosystem, I would say that what characterizes the Finnish, I would say, innovation ecosystem overall, but especially the quantum ecosystem, is that it's very, I would say, closely tied collaboration between the universities, then RTOs, so research institutes like VTT, and then the companies. The ecosystem, of course, also in a small country is in a relatively small, so everybody knows each other, and also our funding agencies, national funding agencies, innovation funding agency, Business Finland especially, is adamant on the collaboration, and typically all the funding that they distribute requires collaboration between these different actors. And when we put this on top of long background on cold temperature physics and quantum technology and superconductivity research from the universities spanning back to the 1960s, and I would say world-class infrastructure both on clean rooms and chip development and fabrication, as well as then on the, let's say, computing infrastructure, both classical supercomputers and quantum computers. We have a quite good position to build quantum technologies from the research to the industrialization and into companies. And this was also recognized just a few months ago when this ESIP published a ranking of worldwide ranking of quantum ecosystems, and this Helsinki region ecosystem was ranked as the #1 in competitiveness in the Europe. And when talking about industrialization, I want to point out the spread of companies that are already active in quantum technologies in Finland, and new ones are startups and are founded all the time, and also existing companies are getting into quantum. So there are many industry, even global industry leaders here, like Blue Force, which is the industry leader on cooling solutions for quantum. And then companies like Modulight and Vexlum, well, they have very specific laser products, but have found a strong market in quantum. And then a lot of in the news in the last few days have been, of course, IQM, who just announced that they will be going public with a quite high valuation of roughly 1.5 billion euros. And overall, I would say in Finland we are in a strong position in quantum, especially in superconducting technologies. We are building in national programs quantum computers, which are really built on I would say very much on a Finnish technology and expertise. The current status being that we have a 50-qubit quantum computer, which was launched roughly a year ago, and launching meaning that it's since then it has been available for researchers and industry users alike for developing then quantum algorithm and applications on it. It's connected also to the supercomputer LUMI, which is in Finland, hosted by the CSC, our center or RTO for scientific computing. And it's the LUMI is one of the fastest, if not the fastest, supercomputer in Europe currently. And overall, this development of quantum computers in Finland in this national development program is continuing towards 300-qubit quantum computers, which will be also hosted at VTT. It's VTT IQM co-development, and we should have these 300 qubits in roughly 2 years. So this is maybe the background of the Finnish ecosystem, and how do we then link this to the European level. So in already mentioned that in the European Chips Act there is several goals and operational objectives, which many of them discuss about the advanced chips for example AI and high performance, the most advanced processors in CMOS. But there is an operational objective on quantum chips, and it clearly states that the goal of the Chips Act is to build advanced technology capabilities for quantum chips, and also to develop pilot lines for prototyping and producing quantum chips. And then if you take a look on the quantum strategy of the EU, which was just half a year ago roughly published, there is a bit different, let's say, wording about the pilot lines. It says that it's emphasizing the industrialization of quantum technology as the role of the pilot lines. So this change in just a few years from prototyping to industrialization also describes that what is the speed of development in the quantum technology field. So in 2 years, it has become much more relevant to talk about actually industrialization and not just prototyping or research in quantum chips and systems. And as a action from this Chips Act goal, the European Union through the Chips JU joint undertaking is creating European quantum stability pilot lines. There are 6 different pilot lines, one for each let's say major quantum platform. So superconducting, photonic, ion traps, neutral atoms, semiconducting, and diamond. And all of these have a common goal of this industrialization of the quantum technology, especially focusing on the chips. So not on the system level. These pilot lines will not be building full quantum computers. They will be focusing on building the most critical building blocks, like the chips that power the quantum computers. So the goal is to develop stable and reproducible chip fabrication technologies, and importantly, provide access for users in Europe, both in academia and industry, for these developed technologies. And these pilot lines consortia have been selected. The pilot lines will initiate during this spring, and it's a 6-year roadmap that has been kind of approved, but the first wave of funding is now given for roughly 3 years for each of the pilot lines, and then there's let's say a milestone, go no go milestone, and then we can apply for the funding for the next 3 years to fulfill the full roadmap for 6 years. And the services, indeed, to provide access for the technologies. That means basically fabrication services, pilot fabrication services, and those will be then coming during the first 3 years from these pilot lines. And I coordinate the SUPREME, the Superconducting European Quantum Pilot Line, so I will give you a bit more details on that one. But before we go there, I would like to summarize all of the 6 pilot lines. So the coordinators of all the other pilot lines were kind enough to give me some information about their pilot lines too, so that I can give you this summary. So as you can see, there is the technology different in all the pilot lines. So they are focusing on a certain quantum platform, and then there are variants under this of needed chip technologies under these platforms. So for example, in superconducting, there are actually different kind of superconducting chip processes, fabrication processes that we develop. 2 ways of making the Josephson junctions, angular operation and etching, and then there's 3D integration, and then some hybrid processes, especially for photonic applications. And similarly, for example, in semiconducting, there is silicon on insulator and then silicon germanium based platforms for the quantum dots. Maybe an exception to mention here is that the photonic quantum pilot line is a bit different because it supports very strongly also ion trap and ion trap and neutral atom platforms, because those platforms are driven by photonics. So it in a sense has 3 different platforms that it supports. But the goals you can read there, but basically all of them go towards the technology maturity improvement. And as you can see on the services column, that all of them are thinking about providing process design kits, which means it's a digital description of your chip fabrication process that the end users can use to design their own chips. And then the pilot lines could fabricate these design chips through this multi-project wafer MPV fabrication runs. Okay, but then I can give you a bit more, let's say, detailed view of the SUPREME pilot line for the superconducting quantum chips that I'm coordinating. So a superconducting quantum chip could look like this. So we have one chip which has actually the qubits in a quantum processing unit. Then there is an interposer wafer which provides, let's say, kind of vertical connections, signal lines to each of the qubits, and then we have a redistribution wiring layer in a third chip, and this is then 3D integrated in a superconducting manner into a single chip stack, which then is actually the quantum processing unit within a quantum computer. In the consortium, we have, I would say, gathered more or less the best know-how in companies and in academia and in research organizations in superconducting technologies in Europe. Noteworthy here is that it's actually more companies than RTOs. So these are very much industry involvement from that perspective, and both small and big companies. There is also bigger foundries like Infineon included, and even though it's more than 20 partners, there will be just a few sites where the chips are then actually fabricated, and many of these companies will then be kind of supporting the companies, and partners will be supporting the process development in these few sites. And indeed, it's coordinated by VTT and myself. So what is then the vision and the goal for the pilot line? It's indeed to develop the stable and repeatable fabrication processes and the 4 different technology flavors already mentioned. And indeed, the focus is in repeatability and stability. So already showed in the first picture how this 3D integrated quantum processing unit comes together. So there you actually need angle evaporated junctions and a 3D integration process. Then the edge junctions work very well for devices that need even thousands of junctions, like the tube amplifiers, readout amplifiers for the qubits, or let's say classical logic like SFQ logic as a coprocessor. And then we need the hybrid processes for optical integration. So we can use it, for example, as for the optical qubit control, or for transducers to connect to optical quantum internet in the future. And then we want to provide the stable fabrication services to users, and our goal is to start already next year this with the first PDKs and MPV runs. And then with these actions, we also are active in building the European ecosystem on development of innovation in superconducting quantum chips, so that we can get this let's say ecosystem in Europe to grow and get more successful companies in these technologies into Europe. But that is where I will stop, and let's go into the discussion with Regis and you all. So as a summary, saying that Finland has a strong quantum ecosystem through let's say a very long background in research and building the infrastructure needed for it, and that this superconducting pilot lines is then in a sense a way to try to duplicate this success on the European level.
Thank you very much, Pekka, for this very detailed presentation. So indeed, we already have one question from the audience, which is a reaction to what you presented. Are there any plan to offer multi-project wafers for ion trap chips at some point? And the question is from Jan Henning Drugs.
Yes, so this is for the TAMP ion pilot line, which is actually coordinated by Silicon Austria Labs. Right. So yes, all of the quantum pilot lines have that goal in at some point of their roadmap to start this kind of a multi-project wafer offering. Now I don't remember by heart if I have date for that, but the Champion, I think they have it in their first 3-year roadmap to get the PD case ready so that they could start this kind of an MPV offering. But don't take that as a ground truth. So yes, all the pilot lines have this goal, but when will that happen? I'm not the right person to say.
So, but the question was at some point. So
at some point, yes.
At some point, the answer is yes. So, you've got a thank you from Jan Henning. Thank you, Jan, for your question. And we have 2 other questions. There's a direct question about the PDKs. Will the PDKs be open source? Question from Luis Miguel Pino.
Of course, again, I can come say this from the perspective of Supreme, and I will say no. They will not be open source from that perspective that they would be kind of freely published. There will be a so-called a license agreement, as is typical for when you distribute PDKs, that you have to agree on. So not fully open source, but of course, if you want to design something to our fabrication services, then the PDK needs to be detailed enough for that.
Mm-hmm. So next question, we have lots of questions. So from Dana Aronovici, which is more oriented towards business. So maybe we can acknowledge a question and we'll talk about that later. It's more about the future of the quantum market. Do you believe there will be enough practical use cases generating sufficient economic value to support a large-scale market? So that's more the question of if we project ourselves with use cases, are there enough use case to generate a large-scale market? What do you think about that?
It's about time scales, definitely. So currently, the market is not there. There is not a use case for large-scale manufacturing. But if we look into the expectations of the growth of both the technology development, so as the technology develops, more applications will open, and then projections of the market growth in especially quantum computing, but overall in quantum chips and also in quantum communication and quantum sensing. I think that it's really not a question if there is, but a question when there is, and that's much harder to say. But the growth rate is very fast currently, so I would say that the time will come.
I have another question from Elizabeth Steinmetz. The question is about and with a focus on the Supreme qubits, the pipeline that you're taking care of. What are the main enabling technologies to achieve industrial quantum systems? Maybe that's the industrial is the key word. And so first question on what are the technologies we have to focus on and how long will it take?
Excellent question. Thank you, Elizabeth, for this. So the enabling technologies is of course a very wide topic. So we can start from for superconductors, a clear enabling technology needed is cooling, and but then there is differences between platforms. For example, the neutral atoms, ions, they need photonics, and to scale those technologies, you have to scale the photonic driving and readout systems. But focusing on the superconductors, then I would say that the enabling technologies include, well, cooling. There is a lot of driving electronics, which is actually room temperature electronics mostly, that is needed. But some part of that electronics could be included inside the cryostat for reducing the number of cabling between room temperature and the cold temperatures. So that could be done using cryo electronics, so cryo CMOS type of chips. Then there is the actual wiring, which is a problem really in the scaling of superconductors. So wiring could be either more innovative ways of doing it in the RF frequencies or going to optical frequencies. So optical wiring between the room temperature and the superconducting temperatures. And then there is what else? Of course, then the whole software stack, in a sense, it's enabling too. Yeah. So that's a good, maybe a starting point.
And what about packaging? Because when you look at the picture that you showed,
Yes,
it's very much hybrid. You talk about cooling, photonics, electronics, and packaging seems to be one of the.
You're absolutely right. Maybe why I didn't list it in the enabling technologies is that I see that especially the 3D integration is so close to the performance of the quantum system that I don't consider it enabling. I consider it to be part of the core. But of course, when you go to to packaging, there's many levels. There's the chip level, then there's module level, device level. So definitely all of these levels, and I think that the device module level packaging is definitely an important enabling technology.
Okay, so we have another lots of questions. So I'll try to take all the questions first. So another question is how to best get in touch with you. We will share your contact details so that you will be easily contacted. So next question from Jeremy Veltin. Do you see possibilities to coordinate between at least some of the pilot lines to have chips that are compatible across modalities and could be integrated into a similar full-stack Q computer? Wow, that's a long question.
Well, yeah. So to the first part of the question, do you see possibilities to coordinate between the pilot lines? Definitely. We are already doing it. As an example, we are working with between the superconducting pilot line and the photonics pilot line to ensure that the photonic components based on superconductors that we are developing and the processes can be then combined to the photonic peaks that they are developing in photonic pilot lines. Similarly, we are talking about how to integrate some superconducting stuff to ion trap activities with the champ ion and the ion trap pilot line. So the coordination is already happening. But then the second part, so that there could be similar components that support many platforms. That's a harder one. Some of the enabling technologies can support many different platforms, but typically in a very deep level, the technical specifications are very different. So for example, a cryo-CMOS chip, the cryo-CMOS technology can most probably support several platforms, but not the same chip. It needs to have a different design, different chip to each platform. Yeah.
Of course. Okay, so thank you very much. Thank you for all your questions. That was from Jeremy Veltin, who says thank you. And you perfectly answered that question, apparently. So he's a happy customer. Everybody is happy today. Yeah, it's contagious. The Finnish happiness is contagious.
Thanks.
So let's proceed with the discussion. And so we understand there was about 10 years of quantum flagship funding. So now we are going into the pilot lines, and you said that these pilot lines are here for the industrialization. So that's a really change of focus. So do you really feel that, and that's close to the question we had before about the business potential. So do you see this transition from research to business today already?
Well, I see that now the window is opening for that. So we already see that there are companies. Of course, the market is still driven by research, but there is already successful companies who are raising a lot of money and selling products in this market. So see that this is now happening, and I think we need both. We should not forget the funding for the research, because clearly there is a lot to be new things to be found out and research questions are there. But then at the same time, we need to ensure that we enable the scaling of this technology into applications. And if we only start thinking about that step when there is already a big market, then somebody else will take that market. So we need to be there already now.
Yeah, and the business in quantum is something, it has reached more than billions today. For
Yes.
US company only, it's 1 billion already. The market is emerging. There's at least a strong interest from corporates to understand that, to connect the quantum computers to supercomputers, like what you just seen in the presentation. And you mentioned also that IQM is going public, so we start to see successes and exits for investors. So that's a very important move also. So that's signs that we are indeed moving towards more a real business economy than full R&D, even though we are not yet in the full deployment of use cases, right?
Yes.
So, and what is the mindset at the moment in the ecosystem? Because is it still collaborative? I see that, for example, IQM and in your consortium, we have Alice and Bob in France, IQM working together. So is it collaborative or is it becoming more competitive with the business orientation?
Well, I think that since it's still a kind of research-driven market, there is still a lot of kind of collaborative spirit. And I think that we are still in this pre-competitive phase from that perspective, that since there is not a clear quantum advantage still demonstrated in, let's say, at least not in many applications. So all the demonstrations of quantum advantage still support the growth of the whole field. So there is a lot of collaborative spirit. But of course, as we move towards shorter and short-term industrial or goals for the companies, then the collaboration comes harder and it becomes more competitive. So I think that we are starting to see more and more competition, but still there is a lot of collaborative spirit.
And because there's also the national investment, we are European, of course, with our national investment, and there might be also a question of sovereignty around quantum technology, right?
Definitely. European sovereignty, I'm not so worried about it. I think on a European level, if you compare, for example, in sovereignty into in AI chips or most advanced processors, then the European sovereignty is not maybe not so good. But on a quantum technology, we actually have a lot of sovereignty already at this point. And that's a kind of strong point where we should also focus, so that we see that this is a critical technology of the future. So we need to invest it into now, so we might then be in a better position than for example in the AI chips currently, so that we don't end up in the same situation. So.
And there's this metric about the number of qubits. We are talking mostly about quantum computing because this is 80% of the venture business today. 80% of the venture capital goes to quantum computing. All the sections, all the different technologies are represented in this 80%. But for all the rest, quantum communications, that's only 20% of the investment. So that's why we are so much focused here. And when we talk about the metrics, we always talk about the number of qubits into a computer. You mentioned IQM with 50 qubits in your presentation. 50 qubits today, is it a physical qubit or logical qubits? How much do you integrate about the error, the quantum errors correction?
Yeah, so that's actually where I have seen maybe even the most development in just in a year or two is the quantum error correction has taken a huge leaps. And currently qubits that we're still talking, they are about physical qubits. So there are demonstrations of logical qubits, even a few logical qubits in the same device, but doing let's say full set of logical operations on a logical qubit level, that's I think there's very rare demonstrations on that one still. So that is a development field where a lot of is happening, and we are not there yet. So before we have full error correction, I would say that it still takes some time. But already with these physical qubits, I'm positive that we will see quantum advantage also in quantum computing in some applications in the during before 2030. Even if we wouldn't have and I think we won't have the kind of, let's say, fully error corrected quantum computer before that.
And what are the strengths in Finland? You mentioned the superconducting technology that you are leading at VTT, but so what are you mentioned a few champions. So what are the strengths of Finland in quantum?
Well, I would say that definitely it's the superconducting technology where we have the strongest position. What I'm very I would say happy to see is that a lot of companies looking into quantum applications, and especially the applications of quantum computing, are being founded, and new companies, also existing companies, are now starting to look into the applications of quantum in their business, and that's kind of another wave of companies and activities that is now initiating, and I find that very, very promising, because traditionally Finnish quantum ecosystem has been very focused on hardware, especially superconductors, but also in the photonics. I mentioned these few laser companies who are
yes, you mentioned Modulite and
tailoring their products to quantum applications and so forth. So it has been very hardware focused, and that's definitely where our strength still lies. But I see now a lot of interesting activities, also spanning from not from the traditional quantum companies, but companies who have been active, for example, in AI, are now starting to look into quantum, and that I think builds on one of the strengths of Finland, which is the application of AI.
So we can see an emergence of new software company more oriented towards applications, including AI and combined AI and quantum. So a few years ago, there was a fear of seeing a quantum winter from the venture capital perspective. So as you are not into venture, but you are an observer of the ecosystem. So do you think that the companies are struggling to raise funds in quantum?
Well, indeed, I'm not maybe the best person to answer this one, but I would say that yes and no. So we see this kind of a bit of focusing that or consolidation also from that perspective, that some companies get a lot of funding, but then others may be struggling a bit. But I don't see this kind of a big quantum winter.
Okay, I did a little bit of research actually on the topic. So I wanted so this is a study that I found from McKinsey and PitchBook, and actually what I see is that the investment globally increases year over year by 50%. It increased from 1.3 to 2 billion from 23 to 24. So there's no winter, there's more money dedicated to quantum. It's mostly in Europe and Asia. So again, something interesting here. And again, 80% towards quantum computing. And the trend is that it seems that this is the top of the funnel, which is supported today. So more emerging companies are supported. younger companies in 24. So we see 21, 30, 37. We can see an increase on the support of younger companies in 2024 compared to the more mature or the scaling companies. So that's indeed, it seems that from the study that I found on the web, there's no quantum winter at the moment, so there's still some investment potential for the young company. I see another question from Elizabeth Scheimetz. How can we make sure we keep the strengths and industrialize quantum computing in Europe? Where do we have the biggest gaps in the ecosystem today? So do you see, in other words, do you see opportunities for new company creation?
Yes, I think that's a good way to formulate it. Well, I definitely see new opportunities in the application layer. So I think that as the technology, underlying technology matures, then if we also think about kind of future markets and compare to, for example, classical computers, then the hardware that you sell nowadays is a very small portion of all the added value created by computers. So of course this will be the case in the long term also for quantum computers, that actually the hardware is not where the most of the value is. The value is in the algorithms and applications, the value in applications. So that's definitely one where there are opportunities. But then do we have critical gaps? How do we ensure that this happens in Europe? That's an excellent question, and I don't have a silver bullet for that one either.
So taking from what you just said, if you said that the value is in the application and we need to find to develop more applications, it goes through the development of the interest of maybe large corporates who could find a use of quantum computing, and so that they can experiment more about quantum computing. So yeah, that's so. Yes. Elizabeth is commenting again. How about the software and design? I think that software, we talk more about the top of the stack, which are more the application areas.
Yeah. That's a very good point, because now even though at least mostly open sourced, one of the most used software platforms in quantum computer is the IBM Qiskit, and again that is of course a US platform. So so this is indeed a very valid question, that how can we ensure that, because this value comes from not being able to finally to fabricate, but to design, and if you again compare the value chain of the classical chips, then the value is in the applications, in the designs, and then actually the SMC's kind of fabrication type of okay, even though it's a huge business, it's actually low margin business. So the big added values are in the higher in the chain, and this software and design are important parts of that one. And there is opportunity there definitely, because the chip, let's say, design chains for the chip design, so the tool chains, they are very immature in quantum, and they are very also heterogeneous between the platforms and also within platform between users. So there is opportunity there to build a winning, let's say, tool chain for the designs, and then also in the I would say all the layers of the software stack, from this let's say how to use quantum computers and also firmware.
We talk more about technology, but what about the talent and skills? Are there difficulties to, do we lack of talent in quantum in Europe?
Well, if you look at the statistics, then actually we are not maybe lacking so much talent in Europe in quantum as other regions are. But of course, this is a growing and a hot market. So there is clearly all the time need to get more experts into the field. And of course, for the technology development itself, it's a long route to make a PhD in physics and to develop the qubits or something very deep into the hardware or into the software stack. But then again, I think that for long term, in the long term approach, we also have to be able to then teach people to use quantum computing and quantum technology, especially quantum computing, in a way that you don't need a PhD in physics to utilize it. So we need to get all the programmers who have a computer science background to be able to use quantum and use quantum computing.
And quantum is indeed very intimidating in some ways. When it's quantum, this is big brain and very complex. But yeah, an engineer can contribute in quantum, even if it's not in the core understanding of the physics behind. So there's a comment this time from Elizabeth Steinmetz. EPOS has started a task force on quantum enabling technologies recently, with the aim to create a common European ecosystem. So unifying new quantum actors and the mature semiconductor players. That's really merging the two populations. Companies interested, please feel free to contact me. So you can feel free to contact EPOS and Elizabeth Steinmetz if you want to join this specific task force on quantum, merging silicon and quantum. Thank you, Elizabeth, for this announcement. All right, so let's talk a little bit about the position of Europe. We talked a little bit about Europe. You said that that we have the possibility to become more sovereign in Europe. You mentioned it before. So do you think it is realistic for Europe to build a full quantum stack from materials and chips to systems and software? You mentioned IBM, which is a US-based company, and it's very well adapted to what you're doing in superconducting, because this is what IBM does. So how do you feel with this full stack in quantum, which would be the full sovereignty of Europe? Do you believe in it? Do you think we can do it?
Well, I think that that there is, yes, a possibility to do that. There is, of course, then also the question that where does it make sense to do it? And I think it's very hard in, this is overall, this is anyhow a semiconducting business. We fabricate the chips using semiconducting fabrication processes and tools and materials. So as we all know, the semiconducting value chain is very, very global. So not only talking about typically fabrication happening in Asia, but also that the tools are many tools are coming outside of Europe and so forth. So the question is also that how wide view you take into the value chain, that where it does make sense to try to do everything fully in Europe, and where it does make then sense to have partners you can trust that handle some parts of it. But I think that there is a lot of possibilities here to build a let's say, if not completely sovereign, then value chain, quantum value chain in Europe that is mostly sovereign, and then is using these trusted partners in some parts.
Let's conclude. We still have 5 minutes ahead of us, so let's conclude with a series of quick questions. So when we talk about technology platforms, we have seen that we have 5 or 6 different platforms: neutral atoms, spin qubits, photonics, trapped ions. So what do you think? Who is going to be the winner? Is there going to be one winner and the winner takes it all, or there will be?
I of course have to answer that it's superconductors.
Superconductor, of course.
But to give a bit longer answer, I think that of course all the platforms have their pros and cons, and I would just like to say that of course the semiconducting platform is ultimately the one that is most scalable. So if they get because it's mostly CMOS, so you can scale that to mass manufacturing like this if they get their qubits and kind of the first steps right. So just want to point that one out. But at this point, I'm not picking winners. I think many platforms will live for a long time in parallel.
Do you think that we're going to have some platforms which will be more adapted to some use cases, or?
Yeah. I think that's completely feasible vision of the future, at least.
So it means that if we have some software companies developing some applications, they almost have to choose the computer they were working on.
Depends on what you're doing, but many algorithms can be ported from platform to another, but then not all. So depends a bit.
Okay. So my last question will be looking forward 5-10 years. So what is a success? What success looks like for Europe in quantum?
Oh, excellent question. I think that in 5 years it should look like a quantum advantage in several, well, separated, but several industrial relevant applications. Then it should look like that we have a growing ecosystem supported by the pilot lines and the design platform activities in quantum, so that we are really growing the industry. And in 10 years, it should then look like so that we have globally leading quantum companies, let them be hardware or software or applications, but we have globally leading companies in quantum in Europe.
Thank you. There's one final question from the audience. Is there any possibilities for new companies to join into current pilot line as new partner? If so, how can it be arranged? And that's a question from Simon He.
I would say that everything is possible if it makes sense. So if there is a really good pitch why the company would need to be inside the consortium and not just as a collaborator or end user outside the consortium, then we can discuss about it. And then it starts with discussing about with the coordinator of that pilot line that you are interested in.
So how can we contact you? What are your contact details? Are there on the slide deck? I can't remember if you're.
I think I have it on the slide deck, so I can.
Okay, so we're going to have the video available on the YouTube channel within the next few hours. So if you didn't have a chance to connect with to pick the email from Pekka, you can just review the content from the YouTube channel. So thank you very much, Pekka, for your time today. It was a very extensive discussion on quantum and Europe. And I really enjoyed the discussion, and I liked the enthusiasm and the happiness around quantum and the willingness to make Europe a leader in quantum technology. So thank you very much.
Thank you, Regis, for having me.
Next session will be next month. We are working on the program. It will be more specifically on photonics. So keep in touch and stay tuned. So thank you for now and see you next time. Bye-bye.
Thank you. Bye.